So let me recap what we talked about on Monday, and then we'll just keep on trucking. So the idea with a triple integral is that we are going to have a function defined throughout a solid object. And to conceptualize it, you can think of your function as measuring the density at each point within that solid object. And if you integrate density, you get mass. So that's kind of our big picture. Integrate density to get mass. And if we do a triple of just a volume differential, a dV, so when you think about dV, in Cartesian coordinates, you're imagining a tiny little parallel pipette, a little rectangular box. If you want to, you could imagine it as a little rectangular cube, where dx is one dimension, dy is another, and dz is another.
Are you recording?
Yes.
Okay. Sorry, I didn't see it. My bad.
Yeah, that is going. No, it's fine. So when you envision dV, you're imagining this little rectangular box. And what we are going to do later today is convert to two different coordinate systems in three-dimensional space. We're going to convert to a cylindrical coordinate system and a spherical coordinate system. So then we're going to have to conceptualize dV in a slightly different way. And what we're going to do with that dV is like what we did with the dA for polar. We took a polar element, and remember that our polar element, it was part of a sector. A polar element was looking like that. And remember we said the area of that was rdr d theta. That's the area of the polar element. So when we convert to cylindrical and spherical, we're going to have to convert the volume. The volume when it's a rectangular box is simple, dx, dy, dz. That is the volume of that little tiny rectangular box. But when we convert to cylindrical or to spherical, we'll have to come up with some correction factor. So this is correction factor in going from dx, dy. So dx, dy is equal to rdr d theta. So r was the correction factor. It allowed us to convert from dx, dy to dr d theta. We just had to multiply by dr. And that correction factor has a name. We'll get to it in a couple of sections. It's called the Jacobian. The Jacobian corrects for a transformation of variables. So when we convert to cylindrical, we're going to have a correction factor, a Jacobian. When we convert to spherical, we're going to have a Jacobian. So we'll get to that later. Right now, when we think about dV, we think of a tiny rectangular box, dx, dy, dz. And when we are working with triple integrals, the innermost integral is always going to represent our surfaces. So if it's dz on the innermost, then we're talking about a lower surface and an upper surface. If dx is on the inside, then we're talking about a back and front situation. If dy is on the inside, we're dealing with a left and right situation. And then the outer two integrals are the ones that we've been doing for the last week. Those are representing the domain of the surfaces. The domain for these surfaces is two-dimensional. So if we have this situation with z, the domain is down in the xy plane. It's some region in the xy plane. And then if x is first or y is first, we do it differently. But that's the idea. So let's keep on trucking. So we were just about to do our first example. So
pretty much what we're doing here is I'm kind of calculating the area between two solids.
The volume between two solids. The volume between two surfaces.
Surfaces, right.
Volume between two surfaces.
And does that, and let's see, that includes surfaces, right.
So now, if we have a triple integral, it's going to represent the volume between two surfaces if there is nothing in here. If there is something in there, then the solid between the surfaces has a function defined on it. So then we're adding up all those function values throughout the solid that's trapped by these surfaces. So we're finding just volume if there's nothing here. But if there is something there, you can say, oh, OK, well, then I'm calculating the mass of the solid object that's defined by these three integrals. So the limits on the three integrals, they define what the solid object looks like. And then either you have a function defined on it or not. If you have no function defined on it, then those three integrals are representing the volume of that solid object. If there is a function defined on it, then the integral is adding up all those function values, and so you can think of it as finding mass. So just like we did with area, we could have a double integral of just dx dy. That gave us area. Which, similarly, if we did a single integral, that also gave us area if we had a function in there. So it's that same idea. If we did a double integral of a function, that found volume. A triple integral of nothing will also find volume. So you have this overlap. There's always going to be a single integral that's going to overlap with the double. There's always going to be a double that overlaps with the triple.
And pretty much triple integrate a function and you get mass?
Mm-hmm.
Okay.
If the function is density, you integrate density to get mass. Yep. So this right here is measuring the density at every point in the solid object that's defined by these three integrals. Then the output is mass. This is the simplest situation where all three limits of integration are all are constants for all three. So then you have a rectangular box. And if we wanted to make sure, let's make sure that we understand, we're saying that y equals 0 to y equals 1. So those are the innermost limits. Those are the surfaces, y equals 0 and y equals 1. So surfaces y equals 0, y equals 1, so that's a left surface and a right surface. And then we restrict ourselves between those two surfaces by looking at the outer two. So x is going to go -1 to 2, and z is last. Z is going -1 to 1. So if we wanted to conceptualize this, we're thinking about these surfaces restricted to this region in the xz plane. So in the xz plane, that's the domain. All right, the domain is always going to, the domain for our surfaces is always the last two variables. Now again, this is the easiest case just because all the limits are constants. If we wanted to reverse them or interchange them, we could do that very easily. With constant limits, no problem. You can move them around. Fubini. So we're going to integrate with respect to y, so we get 3x y squared z, 0 to 1, dx dz. So this is just like we did with the double integral. We just do one at a time, working from the inside out. Nothing but very complicated here. So now the next step is to substitute. We just have to make sure we go in for the right variable. We integrate it with respect to y, so we're going to replace y with those limits of integration. And x and z are held constant. So we're going to get 3x times z.
Shouldn't you do y squared over 2?
I did.
You did.
So y squared, and the coefficient out here is 6.
Oh, gotcha.
So it became a 3. Yeah, sorry, didn't
good.
say it though.
Second. Yeah.
And then we plug in the 1, we get 3xz, subtract off 0, so then we have what we have. Integrate that with respect to x. Fit that over here. So now we're going to get 3x squared z divided by 2 dz, and that will be evaluated -1 to 2. And again, just remember, okay, we integrated with respect to x, so it's these x's that are going to get replaced with the limits of integration. Very easy to goof that up and plug in for the wrong letter. Okay, so then our substitution, we get 4 minus 1, so that's a 3. So we end up with 9 halves z. We're going to agree with that. We have 3z over 2. 3z over 2, that's all constant. We plug in the 2, we get a 4. Plug in a -1, we get a 1. We take the difference, that's 3. And then 3 times 3 is 9. And then, of course, we just integrate with respect to z. So we get 9/4 z squared, negative 1 to 1. Plug in the 1, we get a 1. Plug in the negative 1, we get a 1.
Isn't it 0?
1 minus 1 is 0. So we get a very unsatisfying answer of 0. So,
Box have a massive 0
okay, you tell me.
because it sucks.
It's a bad solid! Okay, hold on, let's answer that question first. So we ended up with a 0. So let's take a look at the limit. Does this surface, let's take a look at, or excuse me, let's take a look at this function. So what this is telling us is that all of the function values throughout this rectangular box add up to 0.
So there's some below.
Some of them are not, we don't want to say below because the box is the box.
Okay.
But some of the function values
Are
are
out of the
negative
box?
with, they're not out of the box, they're still in the box, but some of the function values within the box are negative because it's possible for x to have a negative value, it's possible for y to have a negative value. So there's some of these function values are just as many are negative as are positive, and they just happen to all offset each other.
How can you get a negative density?
Yeah, it's like in that area.
So would this be one that you would interpret as density? Is it possible to have negative density? No. So that concept doesn't make sense here. We use that concept as the placeholder for an application that makes sense. But when we're talking about this being a density function, it wouldn't make sense here, right? Because you can't have negative density. Now, if all these limits were 0 to 1, 0 to 2, 0 to 1, then this would all be positive and we could use that concept. But if you have a function that goes negative, then using density as your placeholder doesn't really make sense.
So in the meantime, we now have a floating cube.
We have a what?
Floating cube, since some gravity can't affect something that has no mass.
Yes.
Yes, exactly. It's just drifting.
Floating.
Drifting. So think of the integral in its basic sense as just adding up function values, right? An integral is adding up function values. Sometimes it has a physical application that makes perfect sense. Those are the things that we usually use as placeholders for meaning. Like when we talk about a single integral, usually the placeholder in our head is that it's finding the area beneath a curve. But if that curve goes like that below the x-axis, then that's not the best sort of placeholder in your mind. You're not finding the area beneath the curve anymore when the curve goes below the x-axis. So then we invent signed area, and we can still kind of keep that in our mind as something that makes sense.
Do you have any suggestions for another placeholder that would work, or no?
In this particular case?
Yeah.
No.
No. Okay.
I mean, because the function's positive in some places, it's negative in other places, and we're just sort of getting the cumulative total.
Okay.
So we'd have to come up with something that can be positive or negative in three-dimensional space throughout a solid. And most of the physical applications, I mean, maybe if we use temperature and we're measuring it in Celsius, some of the spots would have a temperature greater than 0, some would have a temperature less than 0. We could get the average temperature or something,
Okay.
like that.
What about a cost function?
I was thinking that.
Or, yeah, I guess we could think money.
Yeah.
Yeah, we could think money. So somehow, so this is, yeah, we have,
And it holds.
yeah. So we end up with no money. Better than ended up with negative money.
We break even.
Rachel, you got a question?
No, I solved it.
You solved it.
No, my own question.
Excellent.
That's always
I'll have
great.
to stop answering your questions.
Solve them on your own.
You're going to do it on your own. All right, so let's find the volume of this thing. So now here we're finding something very practical. We're finding volume. So we look at the cylinder on top, z equals sine of y. Why do I know instantly that it's a cylinder?
It's missing.
Missing x, right? There's a missing x, so we know it's a cylinder. Anytime there's a missing letter, you're pulling parallel to that axis, so you know you're dealing with a cylinder. So if we graph z equals sine of y in the yz plane, then we pull it parallel to the x-axis. That's going to create a sinusoidal cylinder. And then we have these limits that are also given to us. Y is between 0 and pi, and then we have the planes x equals 0 and y equals x. So you can see those planes, right? y equals x is this line right here. What letter is missing? Z. So then you just pull it vertically. Right, so that's a wall. X equals 0, that's back there, and x equals 0 doesn't really matter in this case because we can't really see it, but x equals 0 is the YZ plane. So we have a wall behind us. When x is 0, we're dealing with the YZ plane. X equals 0 is the equation of the YZ plane. So we've got this cylinder that's bounded laterally by these two planes. So, first question. Well, the first thing is, can we do it this way? Can we do it with a Z on the inside? Is there a unique upper surface and a unique lower surface?
Yes.
Yes. If we drop a vertical element, so in other words, an element parallel to the Z-axis, at every single place that we drop that vertical element, we're going to have the same upper surface and the same lower surface all the way throughout. There's no weird twisting of the surface that creates anything funny. The cylinder is going to be a unique upper surface for every vertical element. The XY plane will be a unique lower surface for every element that we drop. So we can definitely do it this way. And that's always the easiest way because we can visualize that direction easiest. So if we do it that way, then the lower surface is z equals 0, and the upper surface is z equals sine of y. Now we have to deal with the domain for those two surfaces. So we want to look at whatever the region in the xy plane is that defines the domain. So those are defined by y equals x and x equals 0. So y equals x is right there, x equals 0 is right there, and we have this triangle. So that triangle is this triangle down here in the xy plane. So this curve right here is y equals x. This is x equals 0 on that side. And the top is, they tell us y goes from 0 to pi, so the top is y equals pi. This is in the xy plane. So that's our region that we're integrating over. We now have a choice. Do we want to integrate with a horizontal element or a vertical element? It does not matter. In this case, it's going to be pretty simple either way. What do you want?
Vertical.
Vertical is always the more intuitive way to go. So let's go with that. So there's our vertical element. So vertical element means that the constant limits are going to come from which, x or y? X. So we're going to go dy dx, and the x limits are going from 0 over 2. Well, if this is y equals x and that's y equals pi, then this has to be, yeah, that has to be x equals pi right there. So we're going to go from x equals 0 to x equals pi. And then the y's, we look at our element and we have to decide what curves are that bound that element. The lower bound of that element is y equals x. The upper bound of that element is y equals pi. So we're going from x to pi. So that is going to be volume because we're integrating an integrand that's just 1. So that's going to give us volume. The solid object is defined by the limits of the three integrals. That defines the solid object. And if there's no function in here, or the function is equal to the constant function of 1, then you're finding volume. If there's a function in there other than 1, then you're dealing with the density thing or something else. Yeah?
Could I think of, like, when I'm setting this up, could I think of, like, the third one, when you did it, the integral with respect to z, that could be, like, my 3D, like, going up into the z axis. And then the other two are just my bounds in the domain.
That's exactly right.
Is that
That's
what you
exactly
said?
right.
Okay.
So the z's on the inside, that's doing our surfaces, and then the other two are down in the xy plane, which define the region upon which we're going to consider those two surfaces, the subsurfaces.
Would you run into a problem if we took dz, dx, dy, because the dz is in from 0 to sine y? is if you took that integral.
You would just have to solve it first.
So
Or would you just solve for, put an x in there, solve for x, and then solve for y afterwards?
So you're saying, what if we do it this way instead?
Yeah.
Okay, so z is going to be 0 to sine of y. And then if we go with the horizontal element instead, then the y's are going to come from 0 to pi. And the x's are going to come from x equals 0 to x equals y. Like that.
Okay.
So that'll work totally fine also.
All right.
And notice that the y differential is the very last thing we're going to do. So these y's are going to drop into the integrand, and at the very end, we'll integrate them with respect to y.
Okay. Cool.
Yep, totally fine. That will work out absolutely fine. So let's go ahead and do one of them at least. Let's just continue with this one. So now, a couple of things. The outermost integral is with respect to x, right there. Can we collapse this integral
No.
confidently?
No.
No. We can only collapse it if there's no x in the integrand, and we're guaranteed that there will not become an x in the integrand by looking at our limits. But we see that there is an x there, so we cannot collapse it, because there is going to be an x that's going to be generated in the integrand. So we can't do a shortcut there. All right, so let's just go through it then. So first two integrals are that. Now the z, there is no z in here, so we just get the length of the interval, which means the upper limit minus the lower limit, sine of y minus 0. Then we integrate that with respect to y and get minus cosine of y from x to pi. Plug in the upper limit. Cosine of pi, and what's that equal to? Cosine of pi is minus 1, but then we multiply, so we get plus 1. Minus a minus is plus cosine of x dx. And then we integrate that. And this gives us nothing. Sine of pi is 0, sine of 0 is 0, so the only contributor is the x. So our final answer is pi.
Oh, it's so pretty.
So pretty. That number just shows up everywhere.
It's funny when like we're
Well,
doing these
it-
long problems
pro-
and the answer's like.
Well, it's not surprising considering the fact that we're using trig everywhere.
Okay. Did all that work for?
Feels like it. Oh, but it's amazing that we've got this triangular domain, and it's still
And
in.
suddenly it's miraculous.
Yeah, we get pi again. But I'm sure we can come
Again.
up with the geometry, because this line is y equals pi, and that point is pi pi 0. But perhaps not what we would expect. All right, let's do a wedge. So we have this wedge here, and we want to find the volume of this prism. So we have to decide, should we use vertical surfaces? First off, could we use vertical surfaces? If we drop a z line down, do we have a unique top and a unique bottom?
Yes.
Definitely
Right,
unique.
'cause that
slanted piece is always the ceiling, and the flat xy plane is always the floor. Definitely. Could we use an element parallel to the y-axis?
Yes.
Definitely.
We could use all of them.
The left is always the xz, and the front, or the right, is always over here. Right? So if we do an element parallel to the y-axis, we would be going from y equals 0 to y equals 8. Totally fine. And then the domain for that would be back here we'd have a triangular domain back in the xz plane. And then what's our other choice? Front back? Could we do a front back thing? Yeah, we could do a front back thing also. So we could use any one of those three setups. So we've been doing the up-down setup the most, so let's do it a different way this time. Should we do front to back or left to right?
Front to back.
Front to back. So we're going to do front to back, so that means that we're going to put x's on the inside. X's on the inside. So if we put x's on the inside, that means that our surfaces are functions of y and z. we're going to have x equals. We're going to write them as x values. So this plane right here, we have been given it in terms of x and z. We'd have to solve for x. And if we solve it for x, that will give us the equation for that plane as a function of y and z. So we've written that plane as an x value. So we're going to go from the back plane is x equals 0. That's the yz plane. The front plane is going to be minus a quarter z plus a half. Is everybody okay with that? And now the domain has to be in the yz plane. And the domain is back here. The domain is the projection of that plane onto the yz plane, the projection of the tilted plane onto the yz plane. All right, so it's going to be back there. Maybe I should use dots for those. So these go back there. So that's going to be the domain back there. And that's just a rectangle. That's super easy. So that rectangle has constant limits of integration in both directions. And do we want to go dy dz or dz dy? Does that matter? Okay, let's go dz dy.
I agree with that.
So the y's are going to go from 0 to
8.
8. And the z's are going to go from 0 to
2.
2.
So I hear 2 up here. So we want to know right here, when x is 0, what is the z value? 2. 2.
Yep.
So that's going to be up here at 2. That's going to be 0, 0, 2. So that will go 0 to 2.
So when it's a rectangle, you automatically know that both of those outsides are going to be no functions, just
Constants. Yep. Yep.
Nice.
So now if we would have done left and right, it'd be totally different. If we did left and right, the domain would be over here. So we'd have to use a vertical element or horizontal element in that triangle, and we'd have a variable limit. Yeah. Okay, so now when we look at this, can we collapse the y integral here? Yeah, we're guaranteed there's no y in there now. There's no y in these limits, so we can definitely collapse that one. We can't collapse the second one, though, because we're integrating with respect to z, and a z is going to appear. But we can definitely get rid of the outer one. That can collapse to just an 8. Let's come down here. So 8, integral 0 to 2. And integrating with respect to x, there's no x there, so we get the length of the interval. So negative 1/4 z plus 1/2 minus 0. We have that. Then we integrate that with respect to z. To 2. And whatever we get there, so we're going to have, bless you. So we're going to have, what are we going to have? I lost my train of thought. So we're going to have negative 1/2, which is negative 1/2 plus 1, which is 1/2, times 8.
4.
Whoa. All right,
How
get that.
pretty.
Nice integer.
Nice answers today. Yeah.
Nice answers.
Question?
No squares and
Got
square
it.
roots and crap like that.
All right, that's what we're doing. Yep.
Keep going.
Wait a second.
Whoa, wait a sec.
We've got negative 8, right, times 8. That should be 1.
You're saying distribute the 8?
Oh, never mind.
You could do that.
I got it. I got the same way.
Yeah, you could do that too. 8 minus 4. Yep, and it will still work. Still work. Okay, I give up. I won't try. All I wanted to do was try to get rid of that little teeny dot. All right. Now we have a parabolic wedge. Parabolic wedge. Can we put z on the inside? Is there a unique upper surface and a unique lower surface?
Yes.
Definitely. Can we put y on the inside? Yes.
Yes.
Because if we draw an element parallel to the y-axis, the parabolic cylinder would always be the left surface, and the tilted plane would always be the right surface. Could we go back to front?
Yeah.
Yes. Now we're here is one of those harder ones because,
Oh, the trough one.
yeah, it's going to be like going across a trough. Say again?
It's like the positive and negative sides of the square.
Yeah, exactly. So we go from the negative parabola to the positive side of the parabola. That's right. We won't do that way though. Question?
Yeah, so even though it goes through, if we drop the element straight through in the x direction,
Yep.
it's going to hit in two places, but that's okay because they're symmetric.
It's not necessarily that they're symmetric. We know that if we solve this for x, we get x equals plus or minus the square root of y. So the back surface is minus root y,
Yeah.
and the front surface is plus root y.
Okay, so they are unique.
Yep, it's unique. I mean, it's like this. If we went back and forth, if we went across this parabola here,
Oh yeah.
you know, this is always the right curve over here, and this is always the left curve over here.
Okay.
So even though it's the same curve, we can imagine splitting it, and we can come up with an equation for this half and an equation for that half that are unique, so that we don't have a problem there.
So it's like splitting tens in blackjack.
It's just like splitting tens.
What does that even mean?
That means you get 2 extra down cards, and then if you get another 10, you could split again.
Okay.
And long story short, you can make so much money, like that person, where'd they live? That just won the millions or billions of dollars last night?
Someone-
Carolinas, it was one of the Carolinas. It was funny, my wife was going to buy a ticket yesterday, and then she read this story about all these horrible things that happen to lottery winners. You know, this one guy who was, you know, like sued by his wife, and then his children tried to steal the money from him, and then he tried to get, there was an attempted murder on him, and then he ended up committing suicide. And she's like, "We're not buying a lottery ticket." Take my chances.
Wait, if she bought a lottery ticket and she won, does that mean everyone gets an A?
Yes.
That's a time machine.
Time machine. Where's the time
Everybody
machine?
gets an A.
We need a time machine. Okay, so
There's like a better chance
Why does it
that
do
like
that?
watching Michael Jackson.
why does it know what I want to
What
grab?
does the
So
like
funny.
half here and half there, how will that affect the end number?
Say that once again.
Well, our value that we get in the end for evaluating the integral, what will that represent?
It's going to represent the volume because we're not going to. So remember that the integral, the limits of the integral, let's just put these in here. This represents the solid. It's the function in here that is going to mess stuff up if the function is positive or negative. It really doesn't matter if the region itself is in the negative area or the positive area. That's not going to change volume. But if there was a function there, the triple integral of a function would be changed if there were negative values for the variable. But the solid object itself won't be changed. So if we don't have a function in here, we definitely will get the volume, even if it's all below the xy plane, even if it's all behind the xz plane or yz plane, it won't matter. So we will get the volume no matter what. So what about the z? Z goes from
0 to 3 minus y.
0 to 3 minus y. So that's the lower surface and the upper surface. And then to get the limits of integration, we have to look at the region in the xy plane. So let's get that going. The region in the xy plane. So how do we find the region in the xy plane? Let's not put that up there. The region in the xy plane is...
Y equals x squared.
So we take these, so we have the xy plane is z equals 0, so we're going to put z equals 0 in right here to get one of the curves in the xy plane. Right? So this is the tilted plane, and that's the xy plane. So if we set those equal to each other, we'll figure out where that tilted plane hits the xy plane. So that's at y equals 3. So y equals 3. And then we do the other part. We want to know where the cylinder meets the xy plane. Oh, we already know. It's y equals x squared. Right? And so y equals x squared. So we're going to have this. So let's move that thing over here. All right, so that's our region in the xy plane. Is everybody 100% clear on how we get each of those? The simple thing is that cylinder y equals x squared, it has no z in it, so we don't even have to set z equal to 0 because there is no z in it. If we just graph it in the xy plane, we get the so-called generating curve that then is pulled parallel to the z-axis. All right, so now the way I wrote it here, I wrote that y is coming from a constant interval, which means horizontal or vertical element.
Horizontal.
Horizontal.
Why can't we
So
do
that-
vertical?
Should we use vertical instead? That would be
Yes,
easier.
please.
Yes, please. Okay. You were so polite. Because you were polite. Because you were polite, we'll do it. All right, so we're going to do the y's on the inside, x's on the outside. How about the constant interval then?
Negative square root of 3 to square root of 3.
Excellent. Yep. And then how about the middle one?
X squared to 3.
X squared to 3. So the element here, the lower bound is x squared and the upper bound is 3. So that element is trapped between those two y values. Y equals x squared, y equals 3. And then when we look at y equals x squared for the outside, we're trying to figure out what the x value is at the 2 points there. We set x squared equal to 3, and we get x equals plus or minus root 3. Could we use symmetry here? Yeah. We could do this. We could go 0 and 2 right there, and that would work.
I like that.
Yeah, we could do that. So then, let's ask ourselves, can we collapse any integral?
No.
Nah, not in this case. So we have 2, integral 0 to square root 3. And then this one, x squared to 3. Integrating dz, there's nothing in there, so we get the length of the interval. Integrate that with respect to y. We get 3y minus y squared over 2 dx, and that's going to go from x squared to 3. Plug in the 3 first. When we plug in the 3, what do we get? 9 minus 9 halves, so 9 minus 4 1/2, so 4 1/2, I think. So get 9 halves. 9 halves minus 3x squared plus x to the 4th over 2 dx. Integrate that with respect to x. And we end up with something pretty straightforward. So we have 2 multiplied by 9 halves x minus x cubed plus x to the 5th over 10, 0 to root 3. Let's distribute the 2 first, just because that'll make life a little simpler. So plugging in the root 3, let's see, we get 9 square root of 3 minus 6 root 3. Root 3 cubed is 3 root 3 multiplied by 2. And then this one, we get 9 root 3 over 5. Common denominator of 5. Ooh, this thing never ends.
Can we combine the first two first?
Combine the first two, so we get 3 root 3, so 15 root 3 over 5 plus 9 root 3 over 5 is 24 root 3 over 5.
What's the messiest answer then?
Okay, not quite as
Nice.
nice. But
Okay.
yeah.
I have to ask about the exponent thing
Mhm.
again. It's my nightmare this semester.
So root 3 cubed is root 3 times root 3 times root 3. So a pair of them turns into what's the inside. And if we have root 3 to the 5th, we're going to have two pairs. One turns into a 3, the second turns into a 3, and then there's one root 3 left over. So we get 9 root 3.
Can we go over how you got the negative square root of 3 to square root of 3 to be 2 from 0 to square root of 3? Up there.
Right, from here?
Yeah, right. That.
So going from here to there?
Yeah, just the.
So
we
we
pulled the 2 out.
Okay, so this 2's on the front.
Yeah, we pulled it out from the negative
From
square
a-
root of 3 to square root of 3.
So when we plug in this 3 here, we get 9 halves.
No, up a little further. Our limit.
The symmetry thing.
The symmetry thing. Yeah,
Oh,
up
the
there,
symmetry
right
thing.
there,
Sorry.
yeah.
Oh, the symmetry
That's-
thing. Okay, so when we look at our symmetry here and we're talking about the x variable, there's just as much of this parabolic wedge behind the yz plane. There's just as much wedge when x is from 0 to negative root 3 as there is from 0 to positive root 3. Do you see that? So that this plane, the yz plane, is chopping it right in half.
I see how you got
You
it.
see it?
Yeah.
And so because it's symmetric with respect to the YZ plane, so x is measuring the distance from the YZ plane, there's just as much wedge behind as there is in front, so we can go 0 to the front and double it.
Okay, yeah, I see how you got it.
See it?
Yep.
Other questions? Okay, well, let's do that wedge.
Skateboard ramp.
Let's do those. Yeah, that's a pretty stout skateboard
Do
ramp.
you remember tech deck?
What's that?
The
Yeah,
thing is,
my
tech
kids
decks?
love those tech decks, or they used
Yeah.
to. Tech decks, they were totally into tech decks. Tech decks, now they're into other things.
Figure
The tiny
skateboard?
And the other
Yeah.
things.
Now they're into other things. Not tech decks anymore. But skateboard ramps, we still have skateboard ramps,
Those look cool.
but they're not quite as vert as that.
I'm gonna have to bring one in now.
Picture's not to scale. Picture's not to scale.
Not to scale, not to scale. Okay, so we want this solid. Could we use Z on the inside?
No.
No.
No. Could we use Y on the inside?
Yes.
Yes. Could we use X on the inside?
Yes.
Yes. What should we use?
Why?
Y. Okay, let's do it. So we're going to go Y on the inside. So Y on the inside means we're going to use a left surface and a right surface. The left surface is definitely Y equals 0. How about the right surface?
E to the negative.
E to the negative
To
Z.
the Z. Yeah.
E to the negative Z.
Looks like it's kind of.
A little bit. And it's not small.
So does everybody agree those are the front, or the left and right surfaces? Left and right surfaces. And then let's take a look at our domain. So our domain has to be in the XZ plane. So in the XZ plane. And what does that domain look like in the XZ plane?
Rectangle. Wait.
So
And
Right?
Yes.
XZ plane.
exponential.
Right.
So the XZ plane is just a rectangle. So the domain that we're going to consider, because we used right and left, is back here. That's our domain in the XZ plane. So in the XZ plane, what is the Z value on top is 1. And then how far out do we go? How far out the x-axis do we go? 2. So we just have this rectangle in the XZ plane. That's our region that we're going to integrate over.
So then it doesn't matter.
Doesn't matter. So we'll go dx dz, and z's on the outside, so that's going to be 0 to 1. X is on the inside, that'll go 0 to 2.
Nice. I will like
Can we collapse the outer integral?
no.
No, because the outer integral is with respect to z, and there's going to be a z.
If
Could
we
we
done the
collapse?
other one,
We could collapse the middle one, though.
can you collapse?
Yeah, absolutely.
Oh,
Because
it's getting weird.
there's not, right? The middle one is with respect to x, and there's no x's anywhere, so we could collapse it. Let's not do it though. Just
Yeah.
and we'll see
That's
that
a little-
we'll
that's
see
a
that we could.
Shady.
We'll convince ourselves that we could. So we first get this. Oh, look, there's no x there, so we just multiply by 2. right?
Oh, wow.
Right?
Okay.
So that kind of confirms that we could have done what we suggested, and that was to collapse this integral. Yep. So it collapses anyway, because there is no x in that integrand, so we just multiply. This integrand here is constant with respect to x, so we just multiply by the length of the interval. Integrate that with respect to z, we get itself divided by the derivative of the exponent from 0 to 1. So we get -2 multiplied by e to the -1 minus e to the 0, which is 1. So if we multiply this all out, we get 2 minus 2 over e. And that's volume, so that better be positive. Do we agree that that's positive? Yeah, e is about 2.7, so this is definitely a fraction, less than 1. So,
I'll give it E over 2.
so, so this is 1 over e, and then we distribute the 2 to -2. So it'll be -2 over e, and then -2 times -1 to get the 2. Okay. So I think we're about ready for something. Oh, no.
This
not
is the last one.
Oh, no, yeah, this is, yeah, about ready for something a little harder. Okay, so this is harder because we have no clue what that looks like at the moment, and we need to change the order of integration. There's only one way to change the order of integration, and that is to know what you're dealing with geometrically. We need to know. You can't just switch things. That will not work. That will not work. So
A sketch is recommended.
a sketch is highly recommended. So let's think about the surfaces first. So the surfaces are z equals 0 to z equals square root of 4 minus y squared. Now this surface right here, what is that surface?
It's the top part of this circle.
Does everyone agree with that?
How did you know that?
So if we square both
Oh, I know
sides
how
and
you
add
do
y
that.
squared to both sides, this is a circle of radius 2, centered at the origin.
I did.
But because z is non-negative, we know that we're dealing with the upper part of that circle, so the upper hemisphere. And then x is missing, so that upper hemisphere is extruded in the x direction.
Sounds like a bubble looking.
So yeah, so we've got a Quonset hut looking thing, right? Will?
So pretty much, are you gonna want us to, sketch these stuff for the test?
I may ask you to sketch maybe on one of them that's not too complicated.
All right, because usually I just end up using them GeoGebra.
Right, yeah, on the test, maybe one you'd have to sketch. Maybe one.
Of course, again, for these three-dimensional ones, I don't see GeoGebra would be very useful since it just do the outline of it over all the bounds over
when you-
infinity, which kind of make it hard to see the shape.
Yeah, when you're trying to do intersecting shapes, it gets a little complicated.
Yeah, hard to visualize what's going on.
So let's try to get a sense of what this graph looks like. So we're dealing with, we said the upper hemisphere. So that's going to go, or I should say upper semicircle, not hemisphere. Upper semicircle. So we're going to go out to 2 on the y-axis, and we're going to come back this direction 2. And let's use a different color for our semicircle. So it's something like that.
And it's extruded up to 1.
And it's
right?
extruded in the x direction. Okay, so now let's take a look at the other coordinates and see if we can figure out what's going on next. So y equals -2 to 2, and x equals 0 to 1. Okay, so y being -2 to 2 means we are in fact using the entire semicircle. If this just went y equals 0 to 2, then we'd only be dealing with this quarter circle. Okay, but we are using the entire semicircle because y goes -2 to 2, and then extruded out and exactly 1 unit. So we'll come out to x equals 1, and we will have something like that, and to extrude it out.
Oh, wow.
And, so it's a little bridge. A semicircular arch. Okay. And this is a solid object, so I should include this boundary also, just to make sure that we probably could find the volume of this really easily using geometry, right? Area of the semicircle multiplied by 1. And if we're multiplying by 1, the volume is going to be the same as the area. So we just have to find the area of the semicircle of radius 2. Okay, but we're going to use calculus. That'd be too easy. But on the test, when you can use geometry, you're more than welcome to use geometry.
Not that you'll give us one that you can use.
You remember geometry. You remember geometry.
Never.
Okay, so the volume, 0 to 1, negative 2 to 2. Oh, wait, they asked us to switch it. Sorry. They asked us to switch it.
So much.
Yeah, that's not even the question. The question isn't even to find the volume, it's just to switch the order. Okay, so we want to go with an order of dy, dz, dx. Okay, so y's. Oh, this is one like we were talking about earlier where you're going from the negative side of a curve to the positive side of a curve, right? So if y is on the inside, that means we're treating the situation like we have a left surface and a right surface. So the left surface is, what's the left surface?
4 minus some z squared.
So when we solve this for y, we get a left and a right. So y equals negative square root is left, and y equals positive square root is the right surface. So the left surface is the negative part of that cylinder, and the right surface is the positive square root of that cylinder. Does everyone agree with that? Okay, so we're going to go on the inside from negative root of, what was it, 4 minus z squared to positive square root of 4 minus z squared. And now we have to go to the xz plane. The xz plane. So the xz plane, the domain is in here, right? There. That's the domain. So that little rectangle in the xz plane, that is the region where we have a surface to the right and a surface to the left of that. So we have to figure out what that rectangle is. Oh, that's easy. 0 to 1 in this direction, 0 to 2 in that direction. Right? So 0 to 2 goes in the z direction. So 0 to 2, and x 0 to 1. So that is what our, they didn't ask us to evaluate it, they just asked us to switch the limits. Yay. Oh, there's a question.
Yeah. Oh, where did you get the? I didn't see it right away. So the 0 to
Yeah.
2.
Yeah.
That's
So
square.
the circle that we're using to generate the semicircle is the circle of radius. Circle of radius.
2.
The radius squared is at the end.
Oh, 2.
Circle of radius 2. So that's a circle of radius 2, which tells us the distance from here to here is 2.
Oh, perfect. Okay.
Right, so
Because it's centered at
that
the
semicircle back there has a radius of 2. So that tells us the z direction is 2 units and the x direction is 1 because they told us to go 0 to 1 with x. Yeah. Yep.
Well, we could, if we were to evaluate that, we just multiply by 1 and drop off that x.
Yes, we could absolutely, yeah, we could just erase that. So the volume and the area are the same because that direction is just 1. So
And
we
then
could-
also multiply by 2 as well.
no, because that's a z
One.
limit,
And
and z's are going to appear in that integral.
I had my y's and z's switched.
Yeah. Yeah, and so, I mean, this is interesting to just take one more step in here. So the 1s can go away, 0 to 2. Y becomes the length of the interval, which is going to be the positive square root minus the negative square root. So we end up with this. And to integrate that, you would either use geometry or trig sub. So you could use z over 2 equals sine of theta. Yeah.
So
then, can we do the same symmetry thing from the beginning? Like, do we have to do the first, like?
Oh, yeah. This is representing volume. There's no function in here. So we've got to be very careful. If there's a function in there, symmetry is something totally different. Then we have to talk about the symmetry of the function in there. So like you said, we are just finding volume, so we could use symmetry of the solid object. And we could definitely then go from 0 to the right cylinder and then double it. Absolutely. So we could go right here, we could go 0. We could make that, let's use a different color. We could make this 0 and double it there. Absolutely. That would work.
Way easier.
Way easier. But notice what we ended up with. 2 times the upper limit, because this minus gives us 2 times that, or we'd have 2 times the upper limit.
So it's not much easier.
It's the same. It's the same. Okay. All right, let's take a break. Let's take a break.
Should we do the survey thing?
Oh, yeah, do that survey. Triple integrals and cylindricals. So cylindrical is probably going to feel a lot easier than spherical, because cylindrical is just polar with a z. So polar with a z. So we do the r comma theta down in the xy plane, and then we go straight up to the surface. So we have an r comma theta comma z. So when we look at a point given to us in cylindrical coordinates, we have the r comma theta. So down in the xy plane, we do what we would do with polar. And then all we've done is added a z. We've added a vertical variable, a vertical coordinate that measures the height above or below the xy plane. Okay, so that's cylindrical, the idea of cylindrical. The equations that we're going to use to go back and forth between Cartesian and cylindrical, or rectangular and cylindrical. Same equations that we used for polar. The only thing that's different is that we have a third equation, z equals z. So z in rectangular is the same as z in cylindrical.
That's really complicated. Can you go over it again?
No. Yeah, that's the easiest part of these. All right, so the first thing that we always do when we enter a new coordinate system is try to figure out what the shapes are, what the basic shapes are. So our basic shapes, we're going to consider r, theta, and z equal to a constant. One thing to keep in mind is that for cylindrical, we don't have the funky negative r business. So remember in polar, if your r value is negative, you jumped to the opposite quadrant to graph that point. We don't do that with cylindrical. We force the r to be greater than or equal to 0. So we don't have any of that funny business where you go backwards 180 degrees. All right, which is good. That makes it a little simpler. So first, let's talk about r equals k. So r equals k, so that means theta and z are unrestricted. They're not in the equation. That means that those two letters, theta and z, can be anything. So if r is constant, that tells us that we're a fixed distance from the origin. And then, if z can be anything, that means we can go up and down forever. If theta can be anything, and by anything for theta we mean 0 to 2 pi, so that gives us a right circular cylinder, right? So if theta is 0 to 2 pi and z is unrestricted, we're going to get a right circular cylinder of radius k. So that's a very simple way to graph a cylinder, or to write down the equation of a cylinder. R equals 2 is the right circular cylinder of radius 2, centered at the origin. So pretty simple. Theta equals k. So now we're going to rotate to a certain position in the xy plane, angularly, and then r and z are unrestricted. But r has to be greater than or equal to 0, so we can't do the backwards business. So r takes us unrestricted out radially in the positive direction. Z takes us up and down. Up is forever, down forever. So we get a half plane. So we get a half plane, vertical half plane. Vertical, I mean perpendicular to the xy plane. And then z equals k. So z equals k, we go up, that's constant. R can be anything, so that's going to take us radially out as far as we want to go. And theta can be anything from 0 to 2 pi, so that's going to encompass an entire horizontal plane at z equals the constant. And we already saw that z equals z in those equations, so the z for rectangular is the same as the z for cylindrical, and we already know that z equals a constant is a plane. So that's another way to sort of think about it. All right, here is our cylindrical volume element, our dV. And so like I was alluding to before, when our dV is a little rectangular box, it's easy to find the volume of it. Now it's going to be a lot harder.
For 1 second. Okay.
It looks like cheese, is that what you said? Looks like cheese. Looks like cheese. Looks like a wedge of cheese. So
Partially because of the color.
the volume element is going to be represented with r dr d theta dz. So it's the same as the polar area element multiplied by the thickness. So the polar element, we already took care of that. That polar element is giving us this stuff down here. The polar element is this down here. And then we have to multiply by the thickness of it. So that's pretty easy to get to the volume of our cylindrical element. We take our polar element and just multiply by thickness. Easy. So anytime we switch to cylindrical, we switch our dx dy to r dr d theta, and then dz. So this will be very useful if our domain down in the xy plane is a polar region. So we get a polar region, and then we're going to have an upper surface and a lower surface. We will not do polar where we use the xz or the yz plane for our domain. So when we deal with polar, we're going to be dealing with the xy plane, a polar region in the xy plane. So we'll be dealing with surfaces that are oriented in that vertical position, lower surface, upper surface. That's going to be the way we're going to do it. So we have a lower surface, we have an upper surface defined on this polar region.
But if we did, would we just have, so if it was in the YZ plane, we would just pull it in dx, so our x won't change? Okay.
So then the x surfaces, so we have x equals a front surface, x equals a back surface,
So the R
and then our polar region we would have in, r dy dz. Yeah, or r dr, it'd still be r dr d theta, but we'd have a dx instead of a dz.
Okay.
Yeah, it'd still be r dr d theta. It's just that r and theta would be in that back plane, the yz plane. Yep, that's right. That is correct. All right, don't even look at that. That's horrifying. Right. First thing.
Just tell us we're never going to use it.
Yeah, when we switch to polar, you really, we're just, all they're trying to imply here is that you switch your function f so that instead of it being an x, y, and z function, it's an r theta function. So that's all that means, is that in here you have a function of r and theta. That's all that's saying in there. NZ. Because it's cylindrical, not just polar. So all you're doing is switching the x's and the y's to r's and thetas. The z's are going to stay z's, but the r's and thetas will replace the x's and y's. So it looks way more complicated than it is. And then you have your r dr d theta right there. None of us put the r in between the differentials. We usually stick it right there.
Well, because you have to multiply that in
You have to
first.
multiply it with what the function is before you can integrate. So
Well, that's dumb.
yeah, that's kind of weird to put there. Okay, so let's try one. So this is the simplest scenario where all three variables have constant limits of integration. So this is equivalent to the rectangular box thing in rectangular coordinates. So because all three limits are coming from constant intervals, we have a solid object that's a cylinder. So let's integrate. First with respect to z, and if you look in here with respect to z, there is no z, so we just get the length of the interval, which is 2. So our next step is 2 times the integral from 0 to 2 pi. 0 to 1, and then we have our r dr d theta. And yes, we could collapse the outer integral because there's no theta, nor will there be a theta. Should we do that? It's always fun to do that. So that can collapse to just 2 pi, the length of the interval. And then we integrate with respect to r. We get r squared over 2, 0 to 1. So our final answer is going to be 2 pi. And that is representing the volume of this cylinder. It's representing the volume of the cylinder because there is no function in here. Right? The function is just 1. So that means it's representing volume. That R is part of the differential. That's part of the dA thing. So that is representing volume. It's representing the volume of the cylinder. And of course, we could look at it and say, okay, well, the cylinder is too high. So the area of the base, it's a circle of radius 1. So pi r squared gives pi. And then we multiply by the height of the cylinder, which is 2, which gives us 2 pi. So geometrically, it all fits together perfectly. Let's do one of these cone things. Oh, boy.
That looks
Bless you.
Full cone.
horrible.
That looks horrible. It looks horrible in rectangular, but it will look so elegant in cylindrical. Right? It will look so elegant.
Please stop.
I promise. Okay. So to change it to cylindrical, anytime we see an x squared plus y squared,
R squared.
goes to r squared.
So that's R.
So that goes to r squared. So let's go 0 to 3. And then, actually, before I even write this down, let's look at the object a little more before we even go anywhere. So let's look at this and just sort of think about using cylindrical here. So what is when we do cylindrical, again, xy plane is always going to be the r theta domain. It's always going to be down there. So we're always going to be dealing with vertical surfaces. Do you see clearly that the lower surface is z equals 0? Bless you. And that the upper surface is z equals the cone?
Thank you.
Yes.
Yes? Is that a yes? Okay, so the upper surface is this half cone. Well, we're not dealing with a quadric cone. We're dealing with a more traditional cone, half of a traditional cone. Everyone see that? Upper surface is the cone. Lower surface is the xy plane. Okay, what about theta? What do you think theta is going to range between if you look at that?
0 to pi.
Not quite. Oh, no, it's exactly right. Exactly right.
Yes.
I was thinking negative pi over 2 to pi over 2 for a moment.
I'm always wrong.
Yeah, this is the this is the x direction here, so 0 is right there. Yeah, I was thinking that we were going from negative pi over 2 to
That's
pi
a
over 2.
bold statement.
0 to pi. 0 to pi. Totally agree. 0 to pi. How about r? R 0 to
3.
excellent. 0 to 3. So we could probably, if we're trying to, if we know that this is finding the volume of that, I bet we could do this. I bet we could even ignore that and just write down the formula for the volume. We do need to know some numbers, though, so we will have to look at it. But. All right, so let's do it. So the inner one is representing surfaces. I'm going to put the r there. So r dz, dr d theta, so that r doesn't somehow get lost. Let's keep it in front. So the upper surface is the cone, and the cone we find is 9 minus 3r. That's the upper cone, or the upper limit. It's the cone. So all I did was look in here, and x squared plus y squared is r squared. The square root of r squared is r. So that's what a cone looks like in cylindrical. That is the cone. That's a cone.
You can take the square root because you
That's
know it's
good.
positive, right?
Yep.
Okay.
So we know r is positive, so we can take the square root of r squared and get just r.
Oh, yeah.
Yes. Oh, yes.
Yeah.
Okay, next integral, the r. So
Can we double?
this is way simpler than this right here. Can you see what this is doing? This is going from, this is an x, and that's going from the back semicircle to the front semicircle. So it's going that direction. So it's going minus square root to plus square root to go from the back semicircle to the front side of the semicircle. But if we switch it to r, what does r do? 0 to r? R is going to go 0 to 3. And then pi is for this one. 0 to pi for that one.
Oh, that's the angle.
Yep, angle 0 to pi, radial distance starting from the origin going out to a distance of 3. Now, doesn't that look a lot more elegant?
Yes.
That looks so much more manageable. Can we collapse the theta integral?
Yes.
Definitely, we can collapse the theta integral. Can't collapse anything else, but we can collapse that theta integral for sure, so let's do that. And then we integrate with respect to z. There's not a z in the integrand, so we just multiply what's in the integrand times the length of the interval. So are you okay if I write it like that? So the z, we integrate, and we get 9 minus 3r multiplied by r. So we just distribute the r. Integrate with respect to r. So we have pi times 9r squared over 2 minus r cubed, 0 to 3. So we get pi multiplied by 81 halves minus 81 halves minus, that's going to be 27 if we get a common denominator of 54 halves. So whatever that is, 64, 74, 84, so 27 over 2 times pi. That will be the volume of this cone-ish thing.
It's half a cone.
Half cone. Quarter cone.
Half of it.
It's a quarter of a conic cone. Quarter of a quadrant cone. Quarter of a quadrant cone. Half of a traditional cone. Any step there you're not sure about? Tom, you get it?
I like ice cream.
Me too.
These all sound like serving sizes at an overly hip ice cream shop.
Are you
Overly
gonna,
mathematical ice cream.
I'll have a quarter of a quadrant cone.
Have a quiet.
Should be an episode of The Simpsons,
Should
right? Okay, how about this one? All right, so we'll just pretend, I know you guys all know what these surfaces look like, but we'll just pretend you don't.
Is
So-
it bad that I can't see it immediately?
Can you see it immediately?
No.
I mean,
Okay,
will-
so
will-
start on the inside.
Yeah.
Start on the inside. And what is this one?
It's just R.
It's a part of
It's this here.
I've heard nothing correct yet.
Oh,
Is it
no.
circle?
Z squared equals x plus y.
Still haven't heard anything correct.
No,
It's
it's
an
squared
ellipse.
equals x.
Still haven't heard
plus
anything
y.
correct.
It's a plane.
Still haven't heard anything correct. So what do we do when we don't know what a surface looks like? We let substitute x equals 0. We think about traces. So if we,
It's an ellipse.
that's what we should be doing. No, not an ellipse. So if we let x be 0, we get z equals absolute value of y, intersecting lines, except that it has to be positive because of the positive square root. And if we let y be 0, we get z equals absolute value of x, which is intersecting line
Oh,
of
we
v.
get a cone.
We get a cone.
We get two
Cone. Yes, we get a just a regular cone.
Not an elliptic
Oh,
cone?
just one?
Well, we
Because
can
it's
call it an
square root?
elliptic cone, but it's circular. It's
Wait, so we only, are
if
you
we let z
saying,
be 0, we get a point.
are you saying we only get the top
Top half.
cone because of the square root?
Yeah.
Okay.
Yep, that's what I'm saying. Okay, so this is a cone. That's our upper surface. Z equals 4. Oh, actually, that's our lower surface. Lower surface. I think I just said upper. This is lower surface because we're going from here to here. So this is the upper. So Z equals 4 is the upper surface. Z equals the cone is the lower surface. And let's just make sure that this domain out here matches, because if it didn't match, it's possible that we have the cone and then the plane and then some vertical walls. All right? We have to make sure that that cone is intersecting the plane at whatever these two integrals are telling us. So let's check. So y is going from y equals negative square root to y equals the positive square root.
Looks like that could be a radius.
Yep. So this is definitely dealing, if we're in the xy plane, which is where the domain is in the xy plane. So this is going to be a circle of, this is generating a circle of what radius? Radius 4. So let's draw that picture. Let's go into the xy plane, draw a circle of radius 4. And what direction is the element going? So we're going from
Vertically.
so y equals negative, so from the lower semicircle to the upper semicircle. Exactly. Right. So now I drew the element before I analyzed the x's. The x's tell us whether we get the full element or not. So x is going from negative 4 to x equals positive 4. So I guess we have this, what I just said is not quite true. We can draw the full element here because we know we're going from the lower semicircle to the upper. The question is, do we get the whole disk? And the x tells us that we do in fact get the whole disk because we go from negative 4 to positive 4. If the x's only went from 0 to positive 4, we'd have one of those, then we'd have a half cone like the last one. Okay, so now do we have the cone intersecting the plane? Is that the correct domain for where the cone and the plane meet? Does everyone understand what we're trying to decide? Because if the cone is like this, but they tell us that the domain is going to be perhaps smaller in radius than the radius of where the cone would meet the plane. So we could have a vertical wall, right? If the cone is going this way and the plane is up here, there's no reason we couldn't stop, right, and have some
Like a
conical cap to a cylinder. But what happens though with this one? When z is equal to 4, what happens at z equals 4? What do we get here? When we plug z, when we look at where the cone intersects the plane, what do we get?
A circle of radius 4.
So that's going to project the intersection curve onto the xy plane. When we eliminate z right here, when we eliminate z, this projects the intersection curve down onto the xy plane. So we took two surfaces, z equals the cone, z equals the plane, set them equal to each other. That takes where they intersect and drops that intersection curve onto the xy plane. That is matching this exactly. So now we know for sure that the cone is going up and meeting the plane and that there's not some extra volume in between. Okay? So the lower surface is the cone, the upper surface is the plane, and there's no cylindrical wall in between. It's just where the cone meets the plane. Okay, so that is this circle perfectly. Perfectly. We will do one like I am suggesting soon.
Dang.
Soon. Yes, we need to understand all things. Okay, and now let's evaluate this integral. We haven't even started evaluating it. Oh boy. Okay, so let's go to evaluate. Let's come down here. Is it clear that we're finding volume?
Yeah.
Yeah, there's nothing in here, so we're finding volume. Okay, so, and we're going to do it with this coordinate system. So we're going to have an r d z d r d theta. And if we look over here, we can figure out our r and theta quite easily. So we look over here, that's a circle of radius 4. And we're going to go all the way around. So that tells us instantly what the values are for these outer two. We're going to go 0 to 2 pi, and we're going to go 0 to 4. Instantly, right? How about the surfaces? The surfi. It's not even 3. All right, the surfaces. What is the lower surface in cylindrical coordinates?
R squared, root R squared. No.
R. Just R.
R! R it is. Z equals R. Z equals R. Right? That is a cone in cylindrical. z equals r. If you do z equals 3r, it's just steeper. Z equals r is the one at 45 degrees. Z equals r is the cone where that angle right there is 45 degrees and this angle. So z equals r is that perfect cone. And what about the upper surface in cylindrical? Perfect. Yes. Look at that. Worked out so perfectly. Okay. Outer integral, can we collapse it?
Yes, sir.
Yes, we can. So let's chop that thing down. So we're going to have a 2 pi out in front. Leave our middle integral for a moment. The inner integral, okay, there's no z in the integrand, so we're going to multiply the length of this interval, which is 4 minus r times r. So 4 minus r times r. And then we have a dr. And then we get 2 pi multiplied by 2r squared minus r cubed divided by 3, 0 to 4. And we're almost home. 8. Oh, 64 thirds. 96 thirds minus 64 thirds is 32 thirds. 32 thirds, 64 pi over 3.
That's what I got.
Oh, good. We'll go with it. Yeah, so some nasty looking rectangular integrals for simple objects. A cone and a plane are simple. But that looks just horrible. Right? That looks horrible. But as soon as we switch it to cylindrical, I won't say it looks beautiful, but it doesn't look horrible. Looks manageable. All right, let's do more. Oh, a picture. We're such relief when we see a picture. It helps tremendously.
Really? I was more of a fan of the fact that we just had the whole thing written out. I was like, oh, let's go. Play the check.
All right, we'll do another one like that then.
We will?
After this one.
Oh, shit.
We'll do one where we can see it first. We need to break them apart.
This one's in the middle.
Okay, so solid object bounded by a plane and a paraboloid. And we're going spherical. So triple integral, we're finding volume, so it's r dz dr d theta. So there's no function in there other than the r. The r is part of the differential, or it comes with the differential. So that's really a volume integral. And if we want to find the limits for r and theta, we need to figure out where the two surfaces meet and then project that curve of intersection onto the xy plane. So if we set those two equal to each other, what do we get?
It's a circle.
Yeah, we get a circle of radius 5 centered at the origin. Perfect. So that's going to be our domain. And again, with cylindrical, our domains are always going to be in the xy plane, so that kind of simplifies things. And that radius is 5.
Did you say cylindrical or spherical?
Cylindrical. So, yeah, cylindrical. Okay, so z, the lower surface is the paraboloid, and that z equals r squared. Kathy. Upper surface, 25. Everyone okay with that? So the bowl is the lower surface. So that's z equals r squared. Upper surface is that ceiling, z equals 25. R, 0 to 5, and theta,
0 to 2 pi.
0 to 2 pi.
Oh, that's not that bad.
Not that bad.
It's starting to click.
Not that bad. It's not that good, but it's not that bad. Okay, so then we get 2 pi, 0 to 5. Once again, integrating with respect to z, there is no z in there. So we take the length of the interval, 25 minus r squared, multiply it by r. So we get 25r minus r cubed dr. And that will give us the following. Okay, a bunch of 5s in there. So, yeah. All right, so 25 times, let's see, so that's 25 times 25.
625.
625. Oh, and that's 625 also.
Oh.
So it's 625 over 4 right here, I believe. So that's going to be 625 pi divided by 2. Somebody check, but I think that's right.
You got the same answer, just 625 pi.
Just 625 pi?
No,
Oh, no,
no,
no, never mind.
over two.
Okay, good.
Yeah.
Let's make that look more like a 5. All right. So, very important to be able to visualize what's going on with your solid objects.
That's so sad.
Oh, let's go to spherical. Let's go to spherical. Here's where the rubber meets the road. Spherical coordinates.
Yeah, I need somewhere.
But aren't tires cylindrical?
I flipped the page and I was like,
What's
oh,
that?
well,
Aren't
it's back.
tires cylindrical?
Tires are more cylindrical, I guess.
Never specify which rubber, so it could be a rubber.
That could be any kind of rubber, you're right.
Right. That's right. Okay, so cylindrical coordinates are just like polar, but you add a z. Now these are completely different. Completely different. There is one letter that matches. One letter that matches, and the one letter that matches is the theta. It's the one letter that matches. The theta means the same thing in cylindrical as it does in polar, in spherical. Okay, so rho is going to measure the distance from the origin. So that acts kind of like r did in polar. So distance to the origin. Phi is going to measure the distance, the angular distance, rotational distance from the positive z axis. Phi will have a range of 0 to pi. So phi starts at positive z and rotates. It can never go more than pi, though. Theta can go, of course, 0 to 2 pi all the way around. And that's how we can uniquely define a point in three-dimensional space with those three coordinates. If we let phi go 0 to pi, let theta go 0 to 2 pi, and let rho be non-negative. All right? Yeah?
So, like, just be sure I'm visualizing
Mhm.
this right. So you're saying that, like, on the xy plane, theta can go all the way around,
Mm-hmm.
but in the
Vertical plane?
they can only go like half of the semis.
Yes.
Or
Can
a
only-
semicircle.
Semicircle.
Okay.
Yep.
So it can go underneath the XY plane.
It goes underneath the xy plane, and then theta can take you around below the xy plane, and rho can take you away from the xy plane in that negative direction. So you can get to everywhere with those three restrictions. You could let phi go 0 to 2 pi and theta go 0 to pi. That would also get you everywhere, but there's no point in changing theta from what we did with cylindrical. Okay, so let's look at this. This triangle is absolutely essential. That triangle is so important. And what I want to do is draw it from scratch down here because it looks so messy. Let's just draw the essential parts of that triangle that are so important. Because if you understand this triangle, you can do your conversion from cylindrical to spherical in a heartbeat. It is all going to boil down to understanding this triangle. This triangle is spherical coordinates. So we're imagining a point out here. And what we have to do is define, we have to figure out two things. So this is our triangle, and this is a right triangle. That is a right angle right there. So that's a vertical triangle that goes up to our point. And this is R, just like the R with polar or cylindrical. This is Z, and this is rho. So those are the three sides of that triangle. phi sits right here. It's defined to be the angle between the positive z-axis and that radial line, but that's the same angle as this angle because we have parallel lines and a transverse, so opposite interior angles are the same. So those two angles are the same. Okay. Now we can do what we normally do with a right triangle. We can look at cosine and sine of our new angle phi. Cosine of phi is z divided by rho, which tells us z is equal to rho cosine of phi. We can also look at sine of phi. Sine of phi is opposite over hypotenuse, so that's r over phi, excuse me, r over rho. And so then we can get that r is equal to rho sine of phi. So those are our two equations that we are going to use to convert. Because with cylindrical, we have r, theta, and z. The theta we're going to keep. The thetas are the same, but we have to convert the r and we have to convert the z. So here we have rho, phi, and theta. The theta we're going to keep, but we need to convert the rho. We need it from cylindrical. Let me write cylindrical up here. R, theta, and z. So with cylindrical, we're going to keep the theta, but we need to convert the r and the z into rho and phi. And this is how we convert the z and the r into rho and phi. All right, so let's look at these equations now and see if we can understand it. So don't you already know that x is r cosine of theta? You know that so well from polar. X is r cosine theta. Well, that's r right there. R is now rho sine phi. That's r in both those cases. So we just take our polar, x equals r cosine theta, x equals r sine theta, and replace the r with rho sine phi. Right? You know those equations very well. X equals r cosine theta, x equals y equals r sine theta. And then from cylindrical, z is equal to z, but we're going to replace the z with what it's equal to in terms of rho and phi, and that's rho cosine phi. So if you know this triangle right here, you get these two equations, and that does it for us. That and that are everything we need to know to convert from cylindrical over to spherical. So we take our cylindricals, replace r with rho sine phi, replace our z with rho cosine phi, and we've got spherical coordinates. All right. So one thing you should definitely be doing is, and I know when you look here, there's a ton in there. Start with the basics. Practice drawing that triangle and coming up with these equations because you have to have them down or you're going to go nowhere quick. So practice that triangle, and you should get to the point where you can actually visualize, oh yeah, phi's up here in the corner, rho is the hypotenuse, the side that's next to the angle is going to have the cosine, the side that's opposite is going to have the sine.
Would we ever need to use the fact that r squared plus c squared equals rho squared?
This top equation?
Not that top. Well, yeah, that top equation, but instead of x and y, just r squared, because we're not like given rho or something.
Yeah, it's possible that we're given r, and we would have to convert to rho, and so that's absolutely true right here. If we were given this as r squared plus z squared, we would convert it to rho squared. So if we're given cylindrical, it might be quicker to go straight to spherical instead of going from cylindrical back to Cartesian and then to spherical. So we'll see as we go through problems how it kind of plays out. Okay, so basic spherical graphs, same thing we do every time we have a new coordinate system. Rho equals k is a sphere. Rho equals k is a sphere of radius k, centered at the origin. Pretty simple. Phi equals k. So phi equals k, That means that the rotation from the positive z-axis down is a constant. But then theta can be anything and rho can be anything. So we're going to get what we traditionally think of as a cone, half of a quadrant cone. As long as that rotation is between 0 and pi over 2, we're going to get an upward opening cone. If phi is pi over 2, what do we get? A plane. If we rotate pi over 2 and then let rho be anything, that means we can go as far out as we want, and let theta be anything between 0 and 2 pi, we'll get the full xy plane for phi equals pi over 2. Now, if we go greater than pi over 2, so we're going to rotate greater than pi over 2, but less than pi, and we rotate that around, we're going to get a cone that's opening down. Theta equals k. Same thing that we got before. We're going to get a half plane. So theta equals k. We rotate. Rho can't go negative, so we're going to get a half plane in the direction of the angle, the direction of the terminal ray for the angle. So theta equals k will be a half plane.
So rho can't be negative, but
Rho can't be negative, and r can't be negative.
But phi.
Phi is 0 to pi, so it's not negative either. It goes 0 to pi. So there's no negative values for any of those coordinates. All right, the spherical volume element.
Intimidating.
Doesn't that thing look crazy? It looks like we're performing surgery on something. Ooh. All right, so the volume element, we are not going to show why this is true, but the volume element in Cartesian, dx, dy, dz, or some combination. Here, the so-called Jacobian, the so-called correction factor is rho squared sine phi. That is going to be the correction factor when we go from Cartesian over to spherical. So that's all going to be part of the differential, this extra rho squared sine phi. That's just part of the differential when we convert from xyz to spherical. All right, so that right there there's a whole bunch of math involved in figuring out that the volume of this spherical element is that. We won't do that, we're just going to use it.
And that's from Cartesian to spherical?
Cartesian to spherical. So dv in Cartesian is dx, dy, dz. So if we write all three of them up here that we have now, so the simplest one is Cartesian, dx, dy, dz. And then the volume element in cylindrical is r, dr, d theta, dz. So those are our three possibilities for dv, depending on the system that we're in.
And then polar is r, dr, d theta.
Polar is part of the cylindrical, r, dr, d theta, and then we add the dz. So let's do one. Okay, again, looking up here, all they're trying to tell us is that we're taking our function f and we're converting it into a function that has those independent variables, rho, phi, and theta. Those are the independent variables that have to be there. You can't have x's and y's if you're integrating with respect to rho, phi, and theta. So you've got to convert any x's, y's, and z's, you need to convert them over to rho, phi, and theta. And so then they have the function multiplied by the so-called Jacobian. We'll learn that that's called the Jacobian later. So we have our function, we have our Jacobian, and we have our differentials. All right, so let's take a look again. Let's start at the simplest one. The simplest one is where all the limits are constants. Oh, it's not quite constants. Never mind. Simple plus 1. Simple plus epsilon. First question, when we look right here, this tells us that rho is going from 0 to rho equals 4 secant of phi. They're kind of implying that that's a plane. Do we agree that rho equals 4 secant phi is the plane z equals 4? Well, what about if we analyze this by converting this to cosine? multiplying both sides, rho cos phi equals 4. Oh yeah, that's what we call it, that's z. Z is rho cos phi from our picture. So that vertical triangle, the z, has phi right next to it, so that has the cosine of phi. So it's the radius, or rho, which is 4. Let me repeat that. So that vertical triangle, the radius is rho multiplied by cosine of phi. Rho cos phi. That's z.
So that's
Z
that.
equals rho cosine phi.
Right there.
So that's this triangle. I guess it was at the bottom of this page. Where was that?
2.
There. So right there. So z is rho cos phi. So phi is closest to z, so it's rho cos phi equals z. All right, so that is how you represent a plane in spherical. What do you think the plane z equals 10 is going to be?
Phi equals 10 secant.
Rho equals 10 secant phi.
Next one. Yeah.
Yep, rho equals 10 secant phi.
Yep, my
So
brain's-
rho equals constant times secant phi will be a plane at height, whatever the constant is. All right. So, all right, that makes sense then. So we're going from the lower surface, which is rho equals 0, up to the plane. So rho equals, I'm confused now. Rho equals 0, what is rho equals 0? Oh, that's the origin, sorry. I spaced out for a minute. I was thinking cylindrical. I was thinking lower and upper instead of inner and outer. So with rho is our element that's coming out from the origin. So if we were trying to take like a sphere and core out the middle, right, then the inner surface could be a sphere of radius 4, and the outer surface could be a sphere of radius 15 or something. So with spherical, we're talking about inner and outer surfaces, not upper and lower. So the inner surface is just the origin. The outer surface is this plane, and then the cone is generating the lateral sides to the inner and outer surfaces. Okay, so let's go ahead and evaluate this. So coming down here, theta, is there a theta anywhere inside?
No.
No. So let's collapse the outer integral to 2 pi. And then we have 0 to pi over 3. And then we're going to integrate with respect to rho, so we get rho cubed sine of phi divided by 3. And that's going to go from 0 to 4 secant of phi. And we still have our d phi. Everyone okay with that? Rho cubed over 3. And then those limits of integration are being plugged in for rho. Greek letter R.
It's all Greek to me.
I don't like
It's all
letters.
Greek to me. You don't like Greek letters?
They take too long to write. Because I'm a perfectionist.
Oh,
So I
in
go
math
through and I'm
lab,
like,
don't put a P.
oh.
Yeah, it's not a
That-
P. Don't put a P in my math lab. They won't like that. They will not like that. All right, so let's substitute. Let's factor out our constant. And we're going to plug in 4 secant of phi into the rho cubed thing. So 4 times 4 times 4 is 64. And I'm going to convert those to cosines. And put them in the denominator then. And then d phi.
It's just not getting out.
Oh no.
No, I get it.
Looks good, right?
64.
You sub. You sub. No problem.
This is
So everyone understand how it becomes cosine cubed in the denominator?
Where'd your 3 go?
So this is in here.
Oh.
So 64 secant cubed. Secant cubed is the same as 1 over cosine
Do them on
cubed.
the outside.
And that 3 in the denominator jumped out the front and combined with the 2 pi. All right, so now the 64 can come out, and we're going to use u substitution. We're going to use u equals cosine of phi, and du will be minus sine phi d phi. think we should.
It's like little flowers everywhere.
Little flowers. Columbines.
Wait,
Okay.
what? How do
She
we
said
do
the thighs look like
They look like
flowers.
little plants.
all of a sudden I heard Columbine.
Columbines. State flower. Okay, so the 64 comes out, and let's put a minus in front of that. So then sine phi d phi is going to become du in there. So we're going to get integral. Looks like u to the negative 3 times du. And we'll convert our limits back. And we get u to the negative 2 divided by negative 2. We're almost there. So what do we get? 64 pi over 3. U to the negative 2, so that's 1 over cosine squared of phi. And I think phi went from 0 to pi over 3. All right, we're almost home. 64 pi divided by 3. Cosine of pi over 3. Cosine of pi over 3 is 1/2, right? And then we have to square it, so we get 1/4.
That's how that works?
No, it doesn't. It becomes 4.
Yeah.
That's how that works?
That's how that works. That's better, right?
That's
And then
much
cosine
better.
of 0 is 1. So we have a subtraction of 1. So we end up with 64 pi. 64 pi. Cool. Cool beans.
Almost gonna finish.
Frijoles frios.
What's that?
Frijoles frios, cool beans.
Frijoles de bueno.
Okay.
That cannot be right.
That's good
I
beans, but
cannot.
okay.
That cannot be
Good,
right.
but okay.
Good beans.
Cannot be right. We'll go
Okay, I have a question.
Frijoles de bueno.
On the test, would you make us convert, or would you give it to us like they're giving it?
Would I give you the graph?
No, like
Convert what?
your limits.
Frijoles buenos be
Like
good
you know
beans
how
and
in
frijoles
the
buenos
cylindrical
beans
ones
are
we
Yep.
would start with like all this stuff.
Oh
and
yeah,
then
yeah, yeah,
convert?
yeah, yeah.
You'd make us.
I
have
would
these?
give you that other stuff. Some it depends
Only
on the
from the good
problem.
beans
Okay.
stock.
We'll do enough of
Stock
both.
for exile.
We'll do
Will
enough
we
of
do
both.
ones where we have to? Oh,
Yeah.
this one will.
I mean, right now they're just trying to get you used to drawing your Greek letters.
Okay.
We haven't. Yeah, we haven't.
Oh, this one has a function.
We haven't interpreted anything yet. Okay, this one has a function. Great point. So there is a function here. So this is not just volume. Now that is a function that's positive valued. There's no negatives ever going in there. So here's a perfect one to think of that as density. So integrating density to get math. It's even integrating density to get mass, not to get math, to get mass. And it's even rho. Don't we use rho for density?
Yeah.
Do we use rho for density sometimes?
I think so.
Yeah.
Oh, yeah, yeah.
this case
No,
it
like
get
when we were in Calc
confusing.
2.
We did use rho.
We did.
I think so,
Yeah.
yeah.
We didn't use the delta.
We
We
only
used the
did like a
rho.
couple like.
Yeah,
Oh,
rho is mass for
yes,
rho.
we
Use rho
did.
for density.
I remember that now.
I don't know why we would use
Oh, yeah.
rho since
Oh.
that's like an R.
Yeah,
Okay.
I remember that.
All right. So can we get rid of the theta integral first?
Yes.
Yes. There's no theta, nor will there be a theta. Okay. So there's our the middle integral, and then on the inside, doesn't this just all boil down to 1 divided by rho?
Yeah.
Okay. So the integral of 1 divided by rho,
It's a natural log of rho.
natural log of rho. We don't need to have absolute values because rho is going to be positive. Now we still have the sine of phi out there, but we can just sort of ignore, we can move it to the side, I should say. Maybe not ignore it, but move it to the side. So sine of phi, we only have one integral left. All right, so everybody agree with that. So we have rho squared over rho cubed, which reduces to 1 over rho. Integral of 1 over rho is natural log of rho with limits 1 and 2 sec of phi. Outer integral collapse, so that's what we boil down to. So conceptually, notice up here we have rho equals 2 secant phi, so that is the horizontal plane at z equals 2. And then down below we have rho equals 1, so what is that?
What's a plane at z equals 1?
So rho equals 1 is rho equals 1. That's the inner surface. That's rho equals 1, sphere of radius 1.
So that's what that little.
Yeah, that's what this little bubble is. That's the top of that sphere. So there's a sphere of radius 1 right here. So we've got this conical thing with a dimple in it. And so we're going, if we look at our spherical element is from the inner surface to the outer surface. So the inner surface is that sphere of radius 1. Then we're going out to the plane. And then the lateral bounds are the cone bounds. So the inner surface here, sphere of radius 1, outer surface is the plane at z equals 2. All right, so let's plug and chug this stuff. So we get 2 pi, still have this integral. We have to do some nasty log business here.
Oh.
So log of 2 secant of phi minus log of 1. Log of 1 is 0, so that's good. So we have this. But we have that going for us. All
At
right.
least there's one positive thing.
One positive thing going. Okay. What is our integration technique here? Question?
Isn't secant times sine? Oh, that's in the.
Yeah, that's in the secant's inside the log and the sine's outside the log, so we can't combine them.
But it's sine over cosine.
Well, we can write the secant as 1 over cosine and then use substitution with u equal cosine, and then the derivative of cosine will grab that sine. So let's do that. Let's rewrite this. So natural log of 2 over cosine.
Can we use u sub?
Yes, that's what we're going to do right now. We'll use u sub.
Oh.
So u will be cosine of phi.
That's what you're doing?
That's what we're doing. Let's do it.
You think we'll get
So we get that. So that will leave us with integral. Let's see, do we want to convert our limits? Yeah, let's convert our limits. They're easy enough in this case. So there's our statement. If phi is 0, cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. So let's do that. Let's convert, since it's easy. And then we're going to have natural log of 2 over u multiplied by du
Now we're going to kick that negative out
and
front.
kick the negative out front. I think we have it all. All right. Now, what we're going to do is use a log property. So let's split this thing up. So we have natural log of 2 minus natural log of u du.
It rhymes.
Natural log of 2 minus natural log of u du. Oh boy.
Nice.
Yeah.
Oh, wait, I have a question.
That records.
Where'd you get your negative from on the 2 pi?
The 2 came from, the minus came from the differential. We have minus
Oh, right
out there.
Got
So
it. Yep, I even wrote that down.
I like that expression. We kicked it out front. Okay, so then we integrate here. So we have minus 2 pi. Integral of natural log of 2 is just natural log of 2 times u. Can't we just multiply it by the length of the interval? You okay with that? So there's no u in here, so when we integrate this, we just get natural log of 2 times the length of the interval. So root 2 over 2 minus 1. And that's outside of the log. Minus quantity, what's the integral of ln u?
X ln, or I'm sorry, u ln u. Minus U.
Yeah, exactly. Exactly.
And memory is
And that one has to be evaluated still. So let's actually move that just a smidge out. So this piece right here has got to be evaluated still.
Yeah.
Did you just subtract by the?
No, you gotta do it by parts. I just.
So integral of natural log x, remember we did that by with parts.
Yeah.
So
yeah.
integral of ln x dx is x ln x minus x.
Yeah.
Space.
Yeah, so
Memorize
integration
that
by
one.
parts. X ln x minus x.
It's just like comical sounding. Some of this.
Yeah, it's got that nice rhythm to it. Okay, so then we're almost home.
Not really.
Well, you can pretend. Maybe I should have distributed there, I don't know. Okay, so put in root 2 over 2 for the u, natural log of root 2 over 2, minus root 2 over 2, but that becomes a plus. Oh boy. And then we subtract off what happens at 1. Natural log of 1 is 0, so that goes away. We have a minus 1 there. So we have a 1 out here with some sort of sign on it. I gotta figure out if it's plus or minus. I can't keep it all straight. Is it a plus or a minus? All right, so let's see. So if we ignore this minus, it's upper limit.
Minus.
Okay, that distributes. So it is going to end up being a minus, right? That's going to be -1. And then, I'm not convinced. Is it a minus?
Yeah.
Yeah.
You agree? It's a minus? Yeah, I agree. Okay, it's a minus. Because it's a minus, a minus, a minus. It's three minuses. It's three minuses.
Yeah.
3 minus
All right.
equals a minus.
3 minuses is a minus.
The technical term.
Technical terms. All right, and then you can add those numbers together if you just.
Etc. Sounds good. Well, you can also, there's.
Is there cancellations?
There will be a little bit because if you multiply the ln2 across
Mhm.
that, then you will cancel your 2 on the bottom of that first term.
Right, you could separate
And then
this and
you'll-
make this ln root 2 minus
Then you can
ln2,
do
and
that.
there's a whole
Yeah.
bunch of it. All right, let's take a look at one more setup. Setup.
Just the setup.
Just the setup. It's almost 5 o'clock. Almost 5 o'clock. We'll do the setup only. All right, so the solid inside the cone that lies between those planes. Okay, we're going to use spherical. We're finding the volume. Triple integral. Rho squared sine phi d rho d phi d theta. All right. So inner and outer surfaces. The inner surface and the outer surface are both planes. So we're imagining a spherical element. It's coming from the origin, but it's dotted down here because we're not to our inner surface yet. Our inner surface is z equals 1, which we've already seen is 1 secant of phi. Our outer surface is z equals 2, which is 2 secant phi. And then phi is going to go from 0 to whatever that angle is. What do we think the angle is for that cone?
Pi over 4.
Pi over 4. I'll show you why in just a second. Theta, obvious, 0 to 2 pi, because we have a full cone. So this is super important to get. How we got that. That's going to come up. It's not always going to be pi over 4. When we look at our cone here, if we project it into the YZ plane, so we're going to project into the YZ plane, and if I project into the YZ plane, what is x equal to? If I project into the YZ plane, what have I let x equal? 0. So in the YZ plane, we have z equals 0 plus y squared to the 1/2. And we are going to get the absolute value of y. The square root of y squared is absolute y, which is this curve right here. And that perfectly bisects that quadrant, which makes this pi over 4. So if we had a cone that was steeper, we would project into the YZ plane, and we wouldn't bisect here, we would have something steeper. But because we end up with absolute value of y, that bisects, so that's what tells us for sure that that's pi over 4. So if this was a steeper cone, like if there was a 3 out in front or a 4, steeper cone, we would have to figure out our phi by projecting into the YZ plane and figuring out what that phi would be. Figure out phi.
There's so many new words.
Figure out phi. So a lot of times you're going to hear people call it phi or phi, right? But if you're trying to be consistent, you pronounce pi and phi go together. There's other pronunciations that would use p and phi, but we would never call pi p. Europeans call it, they call it p and pi, p and phi, p and p. You know what I mean? We are supposed to use pi and phi instead of p and phi, but a lot of people just mix and mash them. But please don't call pi p in this class. Yeah, Levichevida. Exactly, the Levichevida.
Tensor master.
Tensor.
Tensor master.